today's lecture, we are looking at, as I said, final lecture from me. We are looking at economic analysis and financing of hydrokinetic turbine project. So, as I told you before, it is the economy that is the most important thing. Actually, two things. One is the velocity. You need to high velocity to have a technical feasibility, and then economy. If your product is not economical, nobody will buy it. So, what is the challenge of the economy? Is a high upfront cost. So, you have to invest a lot of money to begin with, and since it is a new technology, you have to convince your regulatory and permitting authority that this is a viable solution. Because when you have a proven technology, it has been using for a long time, getting a permission is not that difficult. But any new technology you bring in, you need to go through this regulatory and permitting hurdles. Recently, I think Indian government has make hydrokinetic turbine is one of the renewable source of energy, is acknowledged or something like that. So maybe in future it will be easier to implement this type of project. So where is the cost coming from? Capital cost. First of all, you have to spend money on turbine, installation, and grid connections. These are the capital cost you have to put up front. When you are running the system, you have operational cost. We call it capex and opex. And the operational cost is maintenance, monitoring, repairs. These are the things happening over 25 years. That's our target, 25 years. Okay. And then revenue. Where is the income coming from? Income coming from energy sales directly. You can get carbon credit, or you may get some government subsidiary or incentives. So you can now look at three different elements. These are your expenses, operating cost. This is your expenses, operational cost, and this is your income. And of course, your income over 25 years has to be more than your cost. Then you have to do cost benefit analysis. Compare cost with your technology against other technology already there. And the way to do it, a simple way to do it is you calculate the other parameter called levelized cost of electricity. That is the term used, levelized cost of electricity. That is the way you compare cost between different electrical generation system. And if your cost is more, obviously you have to do something to reduce it. But sometime if you have government incentives and carbon credit, so maybe in the initially your energy sales may not overcome your cost, but then you have other incentive. And also you have to look at what type of social benefit we are gathering, what type of environmental benefit we are gathering. Environmental benefit is quite apparent. Environmental benefit is quite apparent, because where the remote community, where they are using diesel energy, you can replace diesel energy to include renewable energy. So environmental benefit is quite apparent. Then social benefit. You may think about what type of other benefit you get, because these are the localized system and it can create new type of job there. You can create new type of job related to this turbine installation, turbine maintenance, create new type of job in the local community, and that also have a real benefit to the community. So initially, as I talked about, your capital cost, where is the money coming from? You have to have this part first to cover. Where is that money coming from? Okay. So what are the funding sources? So most of the funding sources is government grants and subsidies to begin with, because it's a new technology, and whether it's commercially viable or not, and lot of money is available for demonstration project. That means a small project, they have put it in the community. You take the technology from your research lab to the community and demonstrate it works. And that type of activities, for that type of activities, there are a lot of government grants available. If there is no grants in India, there is grant jointly with India UK or India European Union. There are lot of call comings to implement this type of technology at a demonstration level. They want to look at technology level that is used. So if you think about, I didn't talk about it, but it's a very important concept. Those who are going into research or already into research, we talk about, have you heard this word? Yes, TRL, technology readiness level. So 1, 2, 3, these are your fundamental research. You are doing it in your research lab. Okay. Then 4, 5, 6, this is what we call valley of death. Valley of death. What happens after doing this type of 1, 2, 3, 1, 2, 3, very fundamental research in the research lab, those technology die. 4, 5, it doesn't go through 4, 5, 6. We call it a valley of death. Technology died. Why? Because there is no incentive, no money to take the technology forward. We have worked it in a small model, like a 3D printed, this size, and you have seen in our fluid dynamics lab, there is a wind turbine of this size. It works. We have proven the technology, but to implement in the ground, you need 2 meter. Yeah, you need electrical connection. We don't have electrical connection in this type of design. We need control. So to take it forward, you need collaboration, because I don't have expertise in control engineering. I don't have expertise in electrical engineering. So we need support from them. And if you don't have, your technology die here. So we call it valley of death. Technology readiness level. We have developed technology, is die. Then 6, 7, 8, if I can come to here, you can, those who are really interested, really high technology, they negotiate with the government grant, with subsidies. There is money from European Union, there is really money from UK, India, joint collaboration. They don't fund fundamental research here. They fund here 6, 7, 8. This is called demonstration in real world. Demo in real world. So that is the most interesting part. Okay, demonstration in real world. We make it big. Where we need collaboration, we cannot do it ourselves alone. We need a big team. Once we get the big team, we can then demonstrate in real world and take data. If real data is successful, then you go into 9 and 10, TRL level 9 and 10. 9 is business proposition, developing your business plan, and 10 is selling your product into market. And this is business planning. 9 is business planning, and 10 is your selling the product into market. So you start off with TRL level 1 to 3. Our friend Mahesh, sorry, what's your name? Rurki from IIT Rurki. Yeah, what's your name? Nitesh. They are doing fundamental research, or professor doing fundamental research. They are here, 1, 2, 3. They are proving the technology. One is the concept, idea. One is concept. Piece of paper, you draw. That is your concept, that is your idea. And you prove that idea by doing computational fluid dynamics, by doing experiment up to 3. This is the 1 to 3. This is actually job of the university in the research lab. But government also want university to break this valley of death. We don't want our technology to die in the lab. We want our technology to take it into field first, field testing. Okay, to do that, there is money. We have to seek money, but we are academic. We are not think that way. Then we have to link up with other, maybe small company, or maybe we create a spin-off company from our university itself, yeah, and take product into market. You see, I am throughout my lecture from the day 1 to now, I am not only focusing on here, right, 1, 2, 3. I am actually trying to take it up to 10. Okay, whole TRL level, technology readiness level. And if you think along that line, that you also make your research more useful, more interesting. Okay, so I start with the concept. I prove the concept in the lab, either doing CFD modeling or experiment. Then my job is finished, but my professor is there. He can create a spin-off company. He can get another PhD project or postdoctoral work, or move the technology, link up with industry and things like that, so that the technology don't die. Most of the thing happen is actually here. Lot of brilliant idea is actually die in the valley of death. We have to overcome that. We have to overcome that by getting money from the government, by European Union or any other sources to demonstrate in real world. Then we have a business plan. Maybe I am not a businessman, but we have to license the product, sells the patent to businessman, and then they have a business plan, and then you start marketing. Okay. So when the private investor coming in and venture capitalist coming in, they may be coming in 4, 5, 6, or even 5, 6, 7, along that line. If I say my technology is here, developed, I tested in real world, so that people will come. So who are the venture capitalists? Have you seen a TV program called Shark Tank or something like that? Yeah, they are the investor. If you go there, you convince them, they will pay you money. Or there are what you call venture capitalists. Lot of people have money. They want to invest in early technology. So risk taker, angel, yeah, angel investor, yeah, they will help you to invest in your early idea. So they may get better profit at the end, maybe 200%, 300% profit. You understand? But you have to convince them. Okay, and there are a lot of entrepreneur innovation pitch. Sometime we have in UK that even our undergraduate student, they just coming up with an idea, just an idea. They go there, pitch it to a lot of businessmen sitting in the front. This is my idea. I want to take it forward. I need this investment. And if they are convinced, they ask and they say there is a potential for this business, they will invest in your idea, and then you take it forward, things like that. You understand? So private investor play a role, and venture capitalist, angel investor play a role, and then other climate fund is there, green bonds is there to fund your project. Challenges is it's a new technology, so high risk. So convincing other people is actually a big challenge. You have to really prove your technology in real world, yeah, and say, okay, I can prove my technology in lab in a small scale, but you really need to prove it in real world, scale it up, real world, and then investor will come. And also you see this type of project has a long payback period, over a long time. We are talking about 25 years it will last. So there is challenge there also. Okay. Now, on top of that, if you have to make this type of technology happen, you have to have convince the regulatory body to get permission from regulator. So there are different body. DEC is one in the UK, FERC in the USA, and then there are other international organizations, IEA and IRENA. They also regulate some of those technology. Why there is a regulation? Why there is a law? Why there is a regulatory body? You have to convince them. You have to get permission from them to install your turbine to ensure environmental protection. You protect the environment. You don't destroy the fishing where fishing is happening. Okay, you just create a turbine in your lab and take it in the river and put it in the river. Okay, you can do it for 5 minutes, 10 minutes, maybe test it half an hour. But if you want to do it long term, your regulatory body will come and catch you, right? Maybe they send you police. Okay, what they are doing, go and check. So 1-2 hours is okay. Don't do long hour, because you have to ensure environmental protection. You have to promote sustainable development and facilitate grid integration. Again, grid, how you connect with the grid? I have no clue myself, because I am not I am a mechanical engineer. I need help from electrical engineer, control engineer, how to connect it into the grid. So after doing my research here in the lab, I just need other support up to this. If you have to prove it in the lab, in the real world, I need support from other people. Okay, I cannot do it anymore alone at that stage. You understand? Working in partnership is very important. Okay, what I wanted to say, regulatory body promotes sustainable development and environment protection. Now, I tell you another story here. So we are doing a project, actually a long time ago, it's a project on sand transport, sand, how the sand flow through pipeline. This was a master's project, so we give it to a group of master's students. And so we are discussing how we can do the project, build up the experimental setup. So our students were interested. So in order to speed up the process of the research, they said, okay, well, let's collect some sand. Let's collect some sand. So what they did, they took 2 buckets and went to Aberdeen Beach and started collecting sand. Problem with Aberdeen Beach is a protected area, because the sand dune there is actually eroding, is going into water. So it's protected area, you cannot take sand basically, and they are caught up by police. And then they say, who are you? So they said, we are RGU student, MSc, and that created a big problem for me also. so I didn't tell them to go and collect sand from them. We can buy sand. Yeah. So that's the issue here. Don't get overexcited and put your turbine in water. Yeah. Somebody will catch you. Okay. Step in permission. How you get permission from regulatory bodies? You have to have site assessment and feasibility study first, environmental impact assessment, public consultation and stakeholder, approval from regulatory agencies at the end. So we discuss everything, right? Public consultation, stakeholder engagement. how you do that. We actually break it down, everything. Those are some of the information you may not find in a book. Those how you do this public consultation. This came through. We did some work, long experience. I collaborated with other social scientists, though those who do this public facing engagement all the time. So some of the information that I presented yesterday gathered through experience working with other partners of my collaborator. Okay, some of these detailed information you may not find in books also. How we do stakeholder engagement. That's actually a very big thing now. Once you done everything, then you apply for permission, and it can take several years. See, that's also a big problem because it's a slow process. If the process is slow, it can take several years. So you have to plan upfront. When is your target to install your hydrokinetic turbine in water? And to do that, you have to get this permission upfront. Okay, so you have to plan accordingly. As I talked about many times, environmental impact, effects on marine ecosystem and fish population. You have to document that. Sediment disruption and water quality, you have to do research and document that. Social impact, community engagement you have to do. You have to convince them these are the benefit. Potential conflict with stakeholder, fishermen, tourism. If there is a potential conflict, you have to resolve that conflict, come up with an agreement, and these are all documented. Everything you have to submit to get a permission from the local authority. They will give you permission. Go ahead, build it there. Okay, so all those work you have to go through. Regulatory challenge, as I said, complexity, because it depends on multiple agencies. You have to go to environmental agency, health and safety. So everything has to be aligned. Health and safety is one issue. Environmental aspect is another issue. Public can stop the work also. Public can stop the work also if they are not happy with the project. For example, in Aberdeen, there is a road, is only 25-mile road. It's called Aberdeen Western Periphery Bypass Road in our town, Aberdeen town. We have a road. That road took 70 years to build. On 25-mile road, 75 years to build. Do you believe that? Why it took that long? Only it hold up by this multiple agency permission. So they do impact evaluation of what's the cost benefit analysis. They got all the money, everything ready, but then some public bring a case saying that you didn't follow the actual process. Then the public lost the case. He took it to High Court. He took it to Supreme Court, and the process went on and on and on. It took only 2 years to build a road, but 70 years it hold up in the planning process. Unbelievable. You cannot build a 25-mile road for 70 years. It's tangled up. 2 generations gone. It's tangled up in the legal process. But it took only 2 years to build. So because it involves a lot of multiple agencies, overlapping jurisdiction. One of the problem happened in the road they put it, there is a frog. A group of frog actually cross the road. Usually they cross across. If they put a road, then what will happen to the frog? They will be killed. When we are crossing the road, car comes and they will be killed. So how we mitigate against that? So they put a path for the frog itself. They are the environmental aspect, like the fish we are talking about, right? And on the road, this is the frog element is there. So you have to come up with some solution so that safely frog can pass. Okay, so there are a lot of, as I said, multiple agency, overlapping jurisdiction. So it incorporate complexity, uncertainty, because it's a new thing. So it's a evolving regulation, and so we don't know the standard. We don't know. Nobody has done it before. You are the first one to do that. So there is uncertainty. So who are evaluating your proposal to put a hydrokinetic turbine, they are also confused what to do, what to make a decision. Cost is high. So high that getting a permission, the more you delay, your cost add up, and delays is a challenge also. Lengthy approval process can stall the project. So if you are waiting for approval for 2 years and you give up, why you take hassle? Move on to something else. Yeah. So these are the challenges of new technology. So how can you overcome this type of challenges? How can you overcome this type of challenges? Early engagement is important. You have to start very early on with all the stakeholder and also regulator. And then streamline the process, advocate for standardized permitting framework. Try to say that, okay, wind turbine is there. We have a process of wind turbine. Why not follow that standard process and give us permission? Because it's though something new, but it's very much similar to wind turbine standard. And demonstrate feasibility and build trust. That's the important thing. Demonstration is very important. Before commercialization, you really need to demonstrate in the real world. And that I talked about in TRL level. This very important. Okay, think along this line. Okay, and also get involved with the government, work with the government to improve regulation. Sometimes you influence the government. If you know the government people, MP, MLA, you work with them. Don't run away from them. Engage with them. Engage with the government office. Influence them. Okay, that will do. So what is the future outlook of the technology? What is the future outlook? Technological advancement. What we need is improved efficiency and reduced cost. Sometimes this cost reduction comes from scale of economics we talked about. Making one is very expensive, but if you make 1,000, 2,000, you set up an industry, you have a streamlined process, you have a recognized supply chain who is supplying your raw materials and things like that, that have a economy of scale. You can have a cost reduction due to massive scale up. Then in order to make this happen, we need support from the government. We try to convince the government this is a good technology, give us incentive, give us money, and make the regulation easy. Make the regulation easy. So try to convince the government. Okay. So you see your job become more and more complicated, right? Initially, when you came here, you thought that my knowledge will be like tea. I will just learn about engineering. Now your job become convincing government, influencing policymaker, try to get money from them. Then you think about global potential. I have developed this technology. Can I export it in other countries? Can I export it to my neighbor, Bangladesh, Nepal, Bhutan? Can I export to Sri Lanka? So that will widen up your business. Maybe you develop in collaboration with other countries. Maybe you develop here, but you demonstrate in Nepal. Nepal might have more water resources and more uh, 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 but don't have the technological advancements that India has. India has a lot of university, lot of colleges, lot of people with a highly talented people, knowledgeable people. Nepal might not have that advantage. So you can then take your technology, collaborate with Nepalese industry or academia. Global potential, not think globally, and also think about, can I integrate and come up with a hybrid system? Can I come up with a hybrid system, something like wind plus hydrokinetic turbine? More innovation. At the same time, at the same structure, can you test wind plus hydrokinetic turbine, integrate with other resources of renewable energy? This will be a very, very interesting research area. Okay, those who are thinking of moving forward into research, this will be another interesting research area. Okay, so what is the final summary we can say in the economic prospect? Economic and finance challenge. There is a challenges to make hydrokinetic project viable for the time being because of economic and financing challenges. Okay, we don't have the attract the money, and this is not a ready-made technology, so you will not get the investor. Regulatory and permitting hurdles, and then you have to come up with your strategy for success. You cannot give up. You cannot say, okay, I tried to come up with an idea, I develop a hydrokinetic turbine, it works in my lab. No, because you have spent quite a lot of time in the lab. You want to take it forward. So you develop your own strategy for success. I cannot tell you which path you need to take. I can tell you what is the process of coming up with different strategy, but at the end of the day, you come up with your own strategy for your success. And a lot of my talk actually went through not technical aspect, but wider aspect of how you can make your project a success or your life a success at the end of the day. So what we need? We need collaboration. Okay, that is actually very, very important. Nowadays, none of the technology you can develop yourself alone. You need to collaborate with other engineers, electrical engineer, civil engineer, maybe river engineers, and maybe your control engineers and things like that, material scientists. Collaborate with industry, with government, with communities, with academia, and finally look in research. Research is key, and look at pilot project, which is demonstration. Don't stop at lab. Try to take that into real river, real water, and that's the important thing. Okay, so now that's the end of my lecture. That is the whole of my lecture. I think today is the last day, and that's the end of my lecture. So I will like to take you back to my first lecture. Just to go back to my first lecture now and see what we covered. So my lecture started on this topic. Okay, I have started giving biography, my university, talked about some of the river, but here I want to stop and talk about, okay, I requested you to think about designing a hydrokinetic turbine for a remote community, and that size will be 5 kilowatt running at 2 meters per second. That remote community is currently relying on diesel generator, which are expensive and environmentally harmful. Okay, now That's the whole idea. During the design process and during my lecture, I was expecting that you will learn these 4 key learning outcomes. One is understand the principle of hydrokinetic energy and how it differs from traditional hydropower. So I will stop here and ask you whether you have developed some understanding of hydrokinetic principles or not after 1 week. If you come up, if some of you already have knowledge, but those who do not have knowledge will come up with a very zero knowledge. Have you developed any understanding of what hydrokinetic turbine is? Okay, good. Next one, analyze relationship between water velocity, turbine design and power output. This is very important. Velocity, velocity, velocity. And how velocity is related to power output, and how then you can design turbine, blade shape, length, radius. Have you achieved that? Some of it? Okay, you understand that? We talked about explore environment and social impact of hydrokinetic turbine. How you can explore social impact and environmental impact. How you do that? Have you got any information related to that? Okay, and that's one we probably didn't do it that much. Develop problem solving and teamwork skills. That we didn't do that. We didn't have much opportunity to do that. But first 3 was the key learning outcome. I hope you gathered that. Yeah. I want to show you something again, going back, how the process start. Process start with initial design sketch. So you take a piece of paper, you draw your turbine design with blade, with generator, mooring system. That's a freehand sketch. And that time you have to think creatively. There are lot of turbine design already available. You can use these as a reference, but you can then think how we can improve that initial sketch. How we can prove that initial sketch? We have a limitation. Limitation is Bayes' law, and that limit is 0.59. Yeah, maximum efficiency 593. Yeah, you are more accurate. Yes, that's the maximum efficiency we can get. That's it. Then we talked about, as I said, environment, economic consideration, impact on aquatic life, fish-friendly design. Okay. Does anybody remember how to come up with a fish-friendly design of a blade? Yes, gradual curve, and then maybe softer material at that tip, flexible material, and also maybe instead of this type of turbine, you have vertical axis turbine. Fish can flow through. Okay. Design based. Okay. Final design. Okay. I will recap little bit more on next little bit of theory, just to recap. I think we have gone through that again. This is the formula actually. This formula help you to do lot of decision making, lot of calculation, decision making, this formula. So very important formula. You can use that to design your blade size from area and then blade size. You can use that formula if you have the design, existing design, that allow you to calculate how much power output you can gain and how many turbine you have to put, and whether that hydrokinetic turbine can serve the community. Because in the yesterday I saw a case from Colombia where we used this simple formula, and we had their power requirement pattern and your power generation pattern, and how that can be matched. Using even this simple formula help you to do a lot of analysis. Let's move on to more complex blade design. and that we did using blade element method. This is your blade. So in that blade you have to decide what type of aerofoil you want to use. You just take simple symmetrical aerofoil, maybe NACA 0.015 or 18. What it gives? It gives you the value of this profile, how that profile will be. X, value of X and Y on a blade, this number. So you take a blade at a particular angle of attack that will have the highest lift coefficient, lift. So maybe your angle of attack you decided 7 degree. You decide yourself and you select that blade. Then your job is to find out how much is this radius, and more importantly, how much is the twist of the blade, because when it is rotating, the linear velocity here is high because radius is high, linear velocity here is low because radius is low. Okay, so you have to balance the actual force equally distributed over the blade. That's why you see very thick blade here, and as you go along, blade becomes smaller. And if you look at this figure, more importantly, this is the longer chord length. That blade has longer chord length, see, and this is smaller, smaller, smaller. This is small chord length. So blade element theory allow you to calculate how much angle of twist you need at each radius, and also how much is the chord length you need. And I have shown you a Python code to help you to design that. You can change the number in the Python code and you can then design a blade. This type of shape of blade that code will generate. How much is the length? How much is the twist you need? Okay, and this angle is also what you call velocity triangle. That is also very important. You start off with two direction of velocity. One is flow direction, velocity of air, and one is say rotational direction, which is omega r. Then you draw a relative velocity, and then you can find out different angle. This one, then you can have a another angle which is called angle of attack, that give you the angle of attack I, and this is the phi angle. These are the angle you have to calculate based on your velocity of air and your rotational speed. That way you calculate all the angle, and the formula for angle is given here. This is the actual formula, and these are the simplified formula. This is the set of formula which is simplified formula that you can use to start off your blade design. What you need, as I said, chord length and angle of twist. These are the two main parameters in that blade element theory. And it has got, I told you, there are a lot of software, QBlade, Harp Opti, those does this blade design. But there is a simple Python code that I wrote, yeah, is available to you after the course, and those Python code you can use to design your blade. Yeah, we talk about vertical axis turbine. This again, the same principle apply here. The challenges here is that you may have a blade here, you may have a blade there. So whatever flow experienced by this blade is undisturbed, fresh air. But after that blade, flow is disturbed. So whatever flow coming into next blade is disturbed. So you have to find out how much is the velocity in the next blade, downstream blade, which is influenced by ADO. Your initial velocity of air velocity, which was coming nicely here, flowing through here, but this blade disturb the flow. Now this blade, what it experiences is a disturbed flow, not the actual air velocity. So how much is the force acting on next one is different from this one, and that shows this calculation, how much is different from the front blade to next blade. And these are all simple algebraic equation. 22 equation is there, right? 23 equation there that can be used one by one, and then you can design this type of Darius turbine. Mainly you calculate power coefficient CP, how efficient they are. So lastly, and this is the computer code we talked about for designing. These are the input parameter here. If you put this input parameter, you will get your output in a blade shape nicely here. Okay, these are the technical part of my course, and I don't want to dynamics, technology, innovation, size selection. Okay, so yeah, that's the technical part of the course. So I don't want to go through any more of any of the design. Yeah, those are the fine. Okay, another area I want to go back to is control, right? I want to go a little bit into control. Okay, so these are the four Python code I have. I would like to share with you. So first of all, as the design code, and this is very nice. You get a chord length versus radius. So that gives you the chord length at different radius. And the important thing to play around is number of blade is 3 here. You can change the number of blade to 4 and see what happens. You can change the water velocity here. I put it 3, you can put it 2 and see how you design it. And this hub, how much hub you need, you can change it and you can design it. Okay, so that's one I discussed before. We talked about this control code, this one, which is your efficiency is changing during the process, and you are trying to control the whole power output using pitch control. And you can see the pitch control after this is so high that your lift force becoming 0 and you don't get the power output here because velocity is so high that it is dangerous to the blade. So that way you can control by changing the pitch angle. And but your efficiency is not 100% during 0.5 to 2 meter per second. That's your rated power and rated velocity. But your cut-in, you can start generating power from 0.5 here, 0.5 meter per second. But then you lose efficiency. You are not running at 100% efficiency in this control technique. You can have other control technique that gives you 100% efficiency here, under 100% efficiency. In this case, you are controlling both pitch angle and torque. How do you control torque? Because the shaft is rotating at a very high speed, you just apply some brake, yeah, to control the torque. Apply more torque, less torque, and things like that. You can see the level of torque changes after this point, but by using torque and angle of attack, you can have high efficiency over the whole operating period. And then I show you another control mechanism, which is actually very random flow happening, very random flow happening. Okay, you can using RPM control, torque control, RPM control also, torque control and pitch control, and you are getting almost uniform power output. Whatever the velocity is jumping around or not, you can get a very uniform power output, where there are some low power output here happening at certain velocity. If the velocity is very low, you cannot do much, your power output is low, but most of the time you have a very uniform power output. So by using a sophisticated control system, you can balance out this fluctuation, this amount of fluctuation you are here in the flow velocity. It can be balanced out. You still get uniform power output by having a complex control system. Okay, so these are the technical part. So I revised the, go back and check the technical part. I hope you can remember this type of technical part. And then I did lot of soft analysis, which is how we can select a location based on map, GIS and things like that. I talked about how we engage with the people, how can set up a workshop with the people. I spent a lot of time on fish-friendly blade design, and also environmental impact, what can happen if you put a turbine in water, what type of impact it can have on the river itself. Those are the technical part. Economics we talked about. So I think we covered health and safety, we talked about safety, risk assessment. So I think we covered almost whole range of knowledge that you need to make this hydrokinetic turbine a successful technology in very near future. Okay, so with this knowledge you can build up your knowledge further, and you try to convince your different stakeholder that this is a good technology, you are passionate about this technology, and you can make this technology happen. Okay, so that's the end of my delivery. I think I will be here whole day. I would like to discuss a little bit about the PhD students to see what type of work they are doing. I'm available on email anytime you contact me. Play with the software. Python code is compiler is free. You can use Google Colab. Somebody told me, right? Google Colab. You take this file and put into Google Colab and run it, and you can generate this plot. Then you change those data, see how it works. Okay, you start out with this design of the blade, 3D plot, 2D plot, play around and see how we can change the blade and things like that. CFD modeling, this is the basic design, but then going into CFD modeling, you have some information on CFD modeling also, that then can help you to do more innovative work. Okay, thank you all for your attention for the last 5 days, and as I say, I will be here and have interaction with you. Yeah, if you have any questions.